Okay, very good morning to all of you. It's a pleasure to really welcome Dr. Vishal Gajjar to speak to us today about fast radio bursts. Dr. Vishal Gajjar is from the Department of Astronomy at the University of California, Berkeley, and he's very closely linked and working with the SETI program. He's one of our former students. He did his PhD on studies of pulsars, emission physics using single pulses from the National Center for Radio Astrophysics, co-host of this Radio Astronomy Winter School under the guidance of Professor Bhalchandra Joshi. He has been passionate about the basic questions that are we alone in the universe since his very young days. And he is working with the Breakthrough Listen initiative, which is also listed in this title page of his. And it's a very comprehensive effort in history, probably the most comprehensive one to quantify the possible distribution of advanced civilizations in the universe. Involves a lot of latest technology, including machine learning, and has made important contributions in our understanding and studies of fast radio bursts. So it's a pleasure to welcome him and invite him this morning to speak to us about fast radio bursts. Vishal.
Thanks, Sax. It is my pleasure actually to speaking to all of you as a part of the Radio Astronomy Winter School. As Sykes mentioned, I was an NCRA PhD student, and I had opportunity to interact with a large number of students over the years when I was there, and it has always been a great opportunity to interact with young curious minds and ask, basically answer their question. So at this talk that I'm going to give today about fast radio bursts, I will likely like it to be as informal as possible. So don't hesitate to unmute your mic and interrupt me at any slide you feel you have any questions. I totally encourage that. That's a right approach because that will also let me know that how much of the thing that I'm currently discussing is being followed, and whether people are actually understanding these things that I'm currently discussing, rather than just me speaking for the 30-40 minutes. So please, as I said, don't hesitate to interrupt me anytime you like. So with that, I like to kind of start with today's discussion. So the topic is fast radio bursts. I don't know if all of you have heard about it. It's very hard to kind of give you the entire picture of what fast radio bursts are and all the different things that's happening in this field within a short span of an hour. But I at least will try to give you a flavor of some of the most meaningful and some of the most sort of interesting discoveries that has happened in this field. And at least I try to kind of answer this question, like what are fast radio bursts and where do they come from and why are they useful? Like what do we do with them? So by the end of it, if you at least get the idea about these three basic aspects of fast radio bursts, I'll be happy that you learned something new from this talk. All right, so before I begin, I like to kind of just give you a picture of what typically we already been doing for last 50, 60 years or so. So we know about this astrophysical object named pulsars. Pulsars have been found in the 60s, and we've been studying them ever since. We now know quite a lot about them. I, in fact, spent my entire PhD thesis in studying pulsars. They are basically neutron stars, highly magnetized neutron stars, which have this emission beam, which is misaligned with their rotation axis. So what you are seeing here on the left-hand panel, you see the rotation axis, which is shown in red, and the white is actually the emission cone. So whenever there is a beam of emission point towards the Earth, you see a pulse like this. So this is a classical sort of our understanding of how pulsars really emit. Although it is not entirely very clear, there are still some debates in our understanding about how this radio emission is being produced. There are some models which currently favored by observation, but there are also other models which may be more suitable. So I'm not going to go into the details of that, but so far I think for this talk, the important fact to remember is that pulsars are pretty good sources for understanding neutron stars. And we've been studying pulsars for last many years. So with that, we were searching for them. It's always a need to find more pulsars, because as you find more and more pulsars, you'll be able to kind of find more details about them. So there were efforts in searching for pulsars. Over the years, people have found that some pulsars exhibit this particular thing called uh, pulse nulling, where pulsars seem to kind of disappear for many, many pulses, which was quite intriguing. And that allowed them to kind of search for more of those objects. But before I move into that, let me introduce you to how do we actually detect them. So what happens is that when these pulses, when they travel through the interstellar medium, due to the frequency dependent of the refractive index of the interstellar medium, the high frequency part of, so these pulses are broadband. When they are actually originated from the pulsar itself, they're broadband. But when they pass through the interstellar medium, the high frequency part of this broadband emission reaches us first, and the low frequency part of the emission progressively gets delayed. And this is what we call a dispersion delay or dispersion. And you can very exactly model it based on the electron density that you were likely to encounter between you and the pulsar. So these are the only equation that I'm going to show you. I'm not going to show you too many equations. I try to keep it as basic as possible. What I'm showing you here is this delta t, which is the time delay between two frequencies. So this is the dispersion that I was mentioning about. You can see the frequency has been labeled here. The high frequency reaches us first, and the low frequency reaches after a few hundred milliseconds. And the time difference, the delta t, is actually the time difference between, let's say, the highest frequency and the lowest frequency. You can very accurately calculate based on this number called dispersion measure. Now, what is this dispersion measure? The dispersion measure is nothing but an integrated column density of integrated electron density. So here we are integrating from 0 to d, where d is the distance to the pulsar. So if you know this, if you know the electron density in the medium between you and the pulsar, you can very accurately estimate the distance of these objects as well. So this is a fascinating thing. Like we've been studying them, and we've been able to basically pinpoint where, or at least have some inference about how far they are. So
I had a
yeah,
doubt in the second slide you showed where you were showing the light curve of the pulsar.
yeah.
The light
Oh,
curve.
here,
Yes, yes. So
yeah.
here I saw that sometimes the cone of the beam widens and sometimes it shortens. So like just now it happened. So why does that happen?
Oh, that is just probably just a visual artifact. I mean, it is just it's a cartoon animation of showing that how, when the beam is pointing towards us, right? I mean, you can imagine it as the beam kind of move towards us, it will become bigger, right? From your perspective, and as it moves away, it will become smaller. It is just
Okay.
a cartoon representation of,
Okay.
yeah. So as I mentioned, that based on the dispersion measure, so this is something we can accurately measure. So when we detect a pulsar, we can measure how much is the dispersion delay. And we have a modeling of the electron density in our galaxy. So we can use that. And based on that, we can actually measure the distances of these objects. So what I'm
Sir,
showing
I
you
have a
here,
question.
yeah, sure.
Yes, sir. So you said for the high frequency pulses reaches the Earth earlier, right? So what would be the probable reason for it?
No, it's just a relative difference. It's not like it is reaches us, and then it is not in the absolute sense. Everything reaches us. Okay, high frequency, low frequency. It is just there is a low frequency part gets delayed as you go to from higher to lower. There is a delay between them, and the reason is the refractive index of the interstellar medium. The cold ionized medium of the interstellar medium has a refractive index, which has a frequency dependence. So as you go to lower frequency, that signal gets more delayed respect to the high frequency. It is just a relative difference.
Yeah, yes, sir. That's what I want.
Yeah. There are so it's not an absolute, it's not in an absolute sense. Everything gets delayed. Even the high frequency one gets delayed. But the relative part of the delay is smaller for high frequency compared to the low frequency. So this is only with respect to each other. Okay.
It helps us to find the distance between what?
Sorry?
You said that it helps us to find some distance. So distance between what?
Between us and the pulsar.
Okay.
Sir, then the pulsars which are in the more inner side of galaxy, so then there will be more delay as
Yes,
there might be more electron density in a line of sight.
absolutely.
Okay, sir.
So what I'm showing you on the left-hand panel here,
I say in those cases, does it become difficult to identify those pulsars, those pulse profiles?
yes, they
Of
are. Yeah, so they do become, they are challenging to find pulsar which are highly dispersed. But at the current modern day technology, we are actually able to find pulsars if they exist at the galactic center as well. So typically, I can give you the number, what is called the DM. Typical pulsar DM ranges from 100 to 200 or so. But if you look at the pulsar, the expected pulsar at the galactic center, that can go as high as 4,000. So only difference for 4,000 is that the dispersion delay now will last not just for a few hundred milliseconds, but for several seconds, depending upon what frequency you're observing, of course. But it is just a matter of sort of correcting for that. So once you know the dispersion measure, the way people do is that they try various different dispersion measure, which we call the trial DM, because at the first time when we are searching for pulsar, we don't know what is the DM. So we try various different DM, and whichever DM gives us the best signal to noise ratio, that is the ideal DM to search for. I'll come to that in a minute. I have a couple of slides on that. So maybe you just wait for one
okay,
or two
sir.
slides. Yeah. Is there any other question?
Sir, what is D pulsar directly proportional to DM?
Sorry?
Sir, there was an expression D pulsar is directly proportional to DM.
Yeah.
So what does it mean?
Oh, D pulsars. I'm sorry, I should have mentioned that. D pulsar is just the distance of the pulsar. So what I meant to say was that the distance of these pulsar is directly proportional to the measured dispersion measures. Does that answer your question?
Okay, sir.
Any other question?
Sir, and what is the small d in the limit of the integral?
I think I mentioned that. That is just the distance from us to the pulsar.
Okay, and the d pulsar is also the same distance.
Any other question?
Sir, and like in the animation you showed it was rotating. So all are not rotating, or all are the same way.
So pulsars are believed to be rotating neutron star. Yes, so all are rotating. Yeah.
But sir, it was in earlier session it was told that many pulsars are observed not to be periodic. So
I'll come to that. So I'm talking about that's the current slide.
okay.
All right. So based on our understanding of their distance, we can place them where they are located in our galaxy. So what I'm showing you on the left plot here, this is our galaxy. Obviously, we can't see it from this angle, but we can say that, okay, if the pulsars are located at least this much away from us, we can place them where they are located. So you can assume this is where Earth is placed. And all the yellow dots are the currently measured pulsars that we've been able to find. According to current model, there are more number of pulsars out there than what we have found. So all the sort of the blue dots that you see are currently kind of just a rough estimate of the expected number of pulsar that is probably out there, which we haven't found yet. So there is a huge amount of effort in the pulsar community to find more pulsars in order to understand them. So far we have found something around 3,000 or so, but obviously their numbers is something of the order of 10,000. So which means that we should be finding more pulsar. Now there are a couple of reasons why people have not yet found pulsar. One of them could be this thing called pulsar nulling. So some pulsar shows this feature. In fact, I spent my entire PhD thesis in studying this one particular phenomena, is that when you expect a pulsar, what do you expect from a pulsar? You expect it to produce train of pulses, but some pulsar switches off like this. It doesn't mean it stopped rotating. It is probably still rotating because it's unlikely to have that much moment of inertia just simply stop for a few seconds and again restart it, right? So it is just simply that some kind of emission processes that is being produced is being interrupted. So maybe this is the reason why we are not finding many pulsar, because they may be nulling. So when we are actually observing them, maybe the emission itself is absent, or there are other effects the interstellar medium add, for example, scintillation, scattering. There could be a whole number of reasons why we haven't found number of pulsars. So there is a huge amount of effort in the pulsar community to find them. So earlier, people were only trying to find pulsar using their periods. So people were searching for pulsars with the rotation period. But now we know that some pulsars do not emit for all the pulses. Sometimes they just simply don't emit pulses. They only emit pulses for fewer seconds, and they switch off. That means that if you take a Fourier transform of a time series like this, you may not be able to detect a pulsar in it. So the other way of finding it is by looking and searching for individual single pulses. And this has given rise to a completely new field, which is what we are going to talk about today, is a fast radio burst. So in 2007, they discovered this phenomena called rotating radio transient, which were also quite intriguing because, as I mentioned earlier, that some pulsar do not emit all the time. Well, this was an extreme case. This was a pulsar which was not emitting at all. They only emitted few pulses, and then at a large amount of time, it remained off. And now we know something around 20 or 30 such rotating radio transient. So there was already an effort to find these kind of more objects, because maybe that can explain the absence of pulsars that we are seeing. Maybe many of them are not emitting regular train of pulses, but just emitting these bright pulses that is hard to detect. So over the year, people have developed tools to find just these single individual pulses in order to find pulsars. So something phenomenal happened in 2007 as a part of the searches. When they were trying to search for pulsars or these individual pulses, they were trying various different dispersion measures, as I said. At one point, they decided to kind of search for dispersion measure, which was not even expected to get from our own galaxy. They said that why don't we search for something that is even further out? And they got lucky. So this was a discovery in 2007. This was done by Duncan Lorimer. They found this one very bright 30 Jansky radio pulse, which had a DM of something around 375. Now, if you actually calculate the dispersion measure you would expect to get if this source was located inside our galaxy, then it was very hard to explain. In fact, the direction towards which this source was found, the distance was at least 8 times further out in the compared to what you would expect from them to be in the galaxy. So what I'm showing, so this was maybe a first indication that there are these single individual bright pulses coming not only from our galaxy, but from outside our galaxy. So maybe there are extragalactic sources which are producing these bright individual single pulses. So the DM that they estimated, the DM distance that they estimated was far larger than any of the galactic sources that they could basically infer, which gave rise to this idea that there are extragalactic bright single pulses. So this was the first discovery of fast radio bursts, and this is where the fast radio burst basically started. Before I move on, are there any questions on this?
Yes, sir. What could be the cause of the nulling pulses?
There are, I think I caught the question. Correct me if I'm wrong. I think the question was, what are the reasons for nulling in pulsar, right?
Yes, sir. What could be possible reasons?
So there are many reasons, or we don't know yet. I mean, as I said, I spent my entire thesis in studying and understanding them. But in my thesis, at least we were able to rule out that it is not any kind of geometric reasons. So there are models that you can divide into something that is intrinsically changing in the pulsar magnetosphere itself. The pulsar itself has I'll come to that. Maybe I'll show you a slide of how does the pulsar emission looks like. So pulsar has an entire magnetosphere, and then you have this radio emission beam coming out of it, right? Maybe the radio emission itself is somehow being seized. Some process is not allowing the radio emission to kind of being produced. That is one reason. The second reason, which they call the geometric model, and there are lots of other geometric models, which seem to suggest that some of these pulsar maybe radio emission cone is being diverted away from you. Maybe due to some effects, the emission cone is not pointing towards you. Maybe it is kind of pointing in another different direction, or there are gaps in the emission beam. So when your line of sight is cutting through the emission beam, maybe you are missing the emission out. So what we did was that we did a simultaneous observation of pulsars across large range of frequencies, and we basically ruled out that the geometry is the reason for pulsar to show nulling. So it's most likely that the pulsars are nulling. They're likely to be the entire radio emission itself is somehow being seized. That's all current understanding I think we have as of this now. We don't know yet why do pulsar null, and if you are interested in it, it's a pretty fascinating field. There is not much happening because we run out of sort of ideas at this point. We are just looking for some more evidence in the observation side of things to give us some clues.
Okay, understood.
Sir,
So why did astronomers start looking for the single pulses? To detect a pulsar.
So if I understand the question, you're saying that why we started looking for single pulses?
Yeah.
So as I said earlier, there were some objects which were found to only emit single pulses. They didn't show a train of pulses. And that is the reason why we decided to look for single pulses to find pulsar.
Oh, okay.
sir, how does the intergalactic medium affect these signals? Is it same as interstellar medium?
I'll come to that later. But
Okay.
yes, it is same. I mean, basically, it's just the electron density that is, but the electron density in the intergalactic medium is far, far smaller than the galactic medium, right? But it does contribute, yeah.
Sir, I have a doubt.
Mm-hmm.
So you mentioned that the astronomers started detecting single pulses for detection of all the pulsars, and the reason being that some of them had this anomaly of some of them had varied pulses in their in the time domain, and that's the reason why they started detecting single one pulsars, pulses of this thing. So how did they get to know that a single pulse is a pulsar itself and not a FRB?
Yeah, good question. It is based on their separation with each other and also based on their dispersion measure. In fact, that is still a question till now. I mean, in fact, when we do find single pulses, when we do searches for FRBs, we have to be cautious that they are not RREX, meaning that they are not pulsar within our own galaxy. And the way you do it is that you basically look at the dispersion measure, and you can calculate what's the expected dispersion measure you are likely to get towards that direction, given the electron density in our galaxy. So we have a pretty good model of electron density in our galaxy, and we can basically infer what would be the expected dispersion measure, even if the source is located at the edge of the galaxy. You know what I mean? So we can find out what would be the contribution of the dispersion measure from our own galaxy. So if you find a FRB or a single pulse with a dispersion measure which is far, far larger than the DM contribution of our own galaxy, that means that it is coming from outside of the galaxy. Does that answer your question?
Yes.
Yeah.
Hello.
Yeah, so I was asking that why do these neutron stars produce the fast radio, like the radio bursts, the radio jets?
You mean the pulsar?
Yes, yes.
I don't have a time to go into that much of a detail, but I can tell you a little bit about it. So the radio emission from pulsar is been a mystery, and there are some clues that we have gotten due to simulations. So what happens is that when these pulsars are rotating, there is a charge potential gap on top of the magnetic axis. So you see the rotation axis, which is shown in red, but the radio emission is aligned with the magnetic axis. So there are regions from which the charged particles are able to escape the pulsar, and which creates the potential gap, which basically is able to pull down charges. So when all the processes are basically coherent emission processes, because none of the incoherent processes can give rise to the bright radio pulses that we are seeing. So, which means that the emission needs to be produced by charged particles moving in some kind of a magnetic field and producing a large number of them, in fact, producing the emissions simultaneously or coherently. So then these emissions are basically produced in a coherent manner in a very small region on top of the pulsar magnetic poles, which are being propagated towards us. And when they travel along the magnetic field lines, they produce curvature radiation, and that gives rise to the radio emission as far as what we have kind of understood. Maybe my explanation may not be sufficiently complete, but I guess that's the general picture that we know about pulsar radio emission.
So why are all neutron stars not pulsars?
So it depends on their magnetic field strength and their rotation speed. There are lots of factors that give rise to this phenomena. Unless they have a pretty good enough magnetic field, they have good enough sort of energies to dissipate, because the radio emission that you are seeing requires energy. So they need to have that much of energy to kind of really radiate out. There are a couple of other factors that come into it. So not all the neutron star is able to produce pulsar. So a fraction of them are able to produce pulsars.
Okay, sir.
So based on the Lorimer bus, or the first fast radio burst detected, there were already hints, there were already clues that maybe fast radio bursts or maybe these individual single pulses are not galactic, they are extragalactic. But this became very clear again, because from 2007 to 2013, Lorimer bus was the only bus, and people were becoming skeptical about the detection, and people were not sure whether that was even a real one. Maybe there was something else, maybe some kind of interference which we are not able to rule out. But in 2013, it became pretty clear that no, indeed, it is an astrophysical. These are astrophysical sources, because 4 more sources were discovered with a similar dispersion measure, which we can't really explain, to come from our own galaxy. So at that point, it became pretty clear that the field of fast radio burst is a sort of a more, I guess that give rise to the entire field of fast radio burst. So what I'm showing you on the left panel are the detection of the four other pulses that were detected in 2013. What I'm showing you in the right plot, this is the dispersion measure, what we call measure dispersion. So what dispersion measure that we have measured for individual objects. And maybe this may answer some of the question, I guess, some of you are asking. On the y-axis, we are showing a ratio of measured dispersion measure against the dispersion measure you would expect from our own galaxy. So as I said, we have a pretty good model of the electron density in our own galaxy. So you can predict how much contribution our galaxy would have in a measured dispersion measure. So these are so you can take a ratio between the two, and you can say that by what factor the dispersion measure is larger. And that way you can say that whether they are galactic or extragalactic. So all the red dots you see, they are all pulsars, and you can see that the ratio is 1. That means they are all within our own galaxy. So we can explain the dispersion measure of all the pulsars that we have found based on the electron density of our own galaxy. While the fast radio bursts are shown with the star symbol, and they have a dispersion measure, the ratio is much larger than 1. Which means that their dispersion measure can be explained to originate from our own galaxy. That means they are likely to be extragalactic. There are also some pulsars that we have detected towards the small and okay, let me recap it. So what I'm showing you in these plots, the x-axis are the measured dispersion of pulsars as well as fast radio bursts. Okay. And on the y-axis is the ratio between the measured dispersion measure against the expected dispersion measure for all these individual objects if they are originated from our own galaxy. So this is the DM versus DM max. That's the maximum dispersion measure the galaxy would be able to contribute or be able to explain. So all the red dots that you see here are pulsars. So they are all below ratio of 1, which means that we are able to explain that they are originating in our own galaxy because their dispersion measures are well within our galaxy. While all the fast radio bursts are shown with the star, and they are obviously above the ratio of 1, which means that their dispersion measures are large enough that we can't explain them to be originated from our own galaxy. So that was the argument that I was making, that you can see that all the pulsars below this line are from our galaxy, while all the FRBs, the dispersion measures are so large that we can't really explain them from the dispersion measure that you would expect from our galaxy. And that's why they are extragalactic.
Excuse me, sir. I have one doubt that the y-axis is just a ratio of the x-axis and a constant. So it should be a straight
It is
line.
not. It is not a constant. Different line of sight gives you different dispersion measure. So it depends on which pulsar you are observing and which line of sight you are actually calculating.
Oh, okay.
Sir, and how do we rule out the possibility that these fast radio bursts might be pulsars, like nulling pulsars of extragalactic origin?
I'll come to that. Any other question on this slide?
So what are SMC and LMC pulsars?
What, you mean the small Magellanic Cloud and large Magellanic Cloud?
Yes, sir.
I mean, these are the kind of our satellite galaxies as a part of Milky Way. These are not like a fully formed galaxy. They are like satellite galaxies, which may be left over from the formation of our galaxy. You see, we have lots of other sort of such smaller galaxies are associated with us, and these are some of the most prominent and the larger one. We can't really see them from where we are located, but if you go to southern skies, like for example, you go to Australia, you could see them. They are bulge objects, and you can see them located at the south of the galactic plane. Yeah. So we have found pulsars in those galaxies as well, but they are not truly extragalactic in some sense because they are still associated with our own galaxy. They are satellite galaxy of our galaxy.
Sir, can you once again repeat what was DM max that divided?
Sure.
Number?
Yeah, DM max for every object, either pulsar or FRB, in that line of sight, you could calculate based on the electron density in that line of sight, what would be the contribution of dispersion measure you would get from our own galaxy. And max means that even if you put the object at the very edge of our galaxy, so that's a maximum dispersion measure you would expect to get from our galaxy.
Okay, sir. And what is that number NE 2001?
That is just one of the electron density model.
Oh, okay.
Okay. So we now know there are thousands of events that's happening in the entire sky in a given day. And we have in fact measured how far they must be coming from. And so we have a volumetric rate of these events in our local universe. So we know that there are roughly around 2,000 of these events happening in a gigaparsec cube every year. So that's pretty good number that we are able to estimate. So somebody was asking this question, like, how do we know they are not pulsars or nulling pulsars in other galaxies? The reason is that the energetics are so large. The total amount of energy that is being produced, given that they are so far away, it's just phenomenal. Pulsars are never known to produce that kind of bright emission. So the energy output that is coming from fast radio bursts are of the order of 10 to the power 42 ergs per second. That's just a high number, but there are some FRBs which go even higher. So, which means that you need to have some kind of a mechanism which is highly energetic. And typical pulsar that we see in our galaxy does not really ever produce pulses of that nature. So we can't really say that the pulsar or FRBs that we have detected are actually nulling or RRATs located in another galaxy because their energies are just not enough. So what else they could be? So then we start thinking about what are the different energetic processes that could give rise to it. Maybe it could be some kind of extreme form of, for example, a neutron star collapsing into black hole, quark star, or maybe it could be evaporating black hole. could be curvature radiation from some kind of a strange quartz star. We don't know. I mean, I'm not an expert on this, so you don't ask me for explanation of it, but these are the theoretical models that's out there. Not just that, there are also models which seem to suggest that it could be some kind of a binary merger. So maybe you will have a neutron star binary, neutron star white dwarf, neutron star black hole, or any combination of this, you take your pick. And any kind of this binary merger can produce extremely bright radio flashes because the energy output, as I mentioned, is so large that you need to go to extremes. So maybe there are some energetic processes which may be giving rise to these fast radio bursts. In fact, something very nice came out very recently that from LIGO detection of gravitational wave, we now roughly know that the number of sort of neutron star merger are of the order of something around 1500 or within a gigaparsec cube per year, which is similar to the rate of fast radio bursts that we are seeing. So maybe fast radio bursts have some association with neutron star binary merger, but we don't know that very clearly yet. It could also be that neutron star, for example, interacting with some kind of a supernova remnant associated with the binary companion. There are whole lots of theory out there. So as of now, let's say this was a case in early 2014 and 15, or I think even before 2014, where we had only few handful detection, and we were trying to explain them. And obviously we went to extreme, and there are lots of models which kind of explain the fast radio bursts with some of the most extreme phenomena that we are known to that were known to happen at that time. So the progenitor model of fast radio bursts largely remain unconstrained due to poor localization, because most of the fast radio bursts so far were detected using single dish telescopes, and single dish telescopes are not really ideal to localizing where they are coming from. Like, for example, I'm showing you an image of here. You all know the Hubble deep field, which is like, let's say 2.5 or 2 arc minute in sort of area, right? It's a pretty small area of the sky. But as you know, that when Hubble kind of took like a week or long observation of that field, they found like hundreds of galaxies or thousands of galaxies in that same area. Now, let's say you found an FRB with a few arc minute error region. So you don't know where it's coming from, because single dishes actually look at several arc minute region in the sky. So when you detect a FRB with single dish, you don't know where exactly it's coming from. You can say that, okay, it is coming from this few arc minute circle. So typically, a few tens of arc minute region tend to have thousands of galaxies in it. So we don't know which galaxy, for example, the FRB might be coming from. And that really was a mystery because we had never been able to localize it until we had something pretty phenomenal that we found. So in 2016, there was an announcement that there was one FRB which was different than the rest of it. All the other FRBs seem to just produce one bright burst and then disappear. Then you never hear from them again. But there was just one FRB which seemed to repeat. Now that's just mind-boggling. Like the energetic that I talked about, it is being able to produce it not once, but multiple times. So when people started looking at the same part of the sky for a long duration, they started noticing that this one FRB, it was producing multiple bursts over the course of many months, which was something very special. And that is what we call a repeating FRB. So before I move on, are there any questions till now?
Yeah. How do you get the energetics?
Mm-hmm.
How do you get this energy, that the numbers that you mentioned, 10 power 42 ergs per second? How do you get that?
So based on the dispersion measure, you can estimate how far, based on what the electron density in the intergalactic medium, the dispersion measure from our own galaxy, and contributing that, we can estimate roughly how far away they must be. And when you measure, what you measure, I think you all kind of heard Nissim's talk, right? We measure these objects in Jansky. So when we detect them, we measure how much Jansky they are bright. Once you know them in Jansky, once you know their roughly estimated distance, you can measure what will be their luminosity. And that's how the energetics were roughly calculated.
Okay. Thank you.
So then for a baseline, what are the energetics of pulsars, like regular normal pulsars?
I'll come to that. Wait for it. Yeah.
Sir, in case of this repeating FRBs, like is there any kind of periodicity involved, or it is like that it is producing repeating radio bursts randomly?
I'll come to that.
Okay.
Any other question?
Sir, I have a question from the beginning part of the presentation. So over the years, you said that astronomers started looking for these, single pulsars coming from the pulsars. So before that, how were actually these pulsars detected? I mean,
Yeah. So earlier, what people used to do was that they used to do. I mean, obviously nowadays also you do the same thing. There is nothing has changed. We just added a new tool. So along with the traditional tool by which you find pulsar, we are also searching for pulsar using a different tool by looking at single pulses. So the traditional tool is that you look at the dispersion, you do the trial dispersion measure. So if you remember that pulses have dispersion, you try a different dispersion, and then you collapse all the frequencies together, and then you have a time series. Now, if you have a pulsar, then that time series will have a periodic pulses in them, right? So if you take a Fourier transform of the time series, you will get a periodicity. Is that clear?
yeah, okay, got it, sir.
So that's how we find pulsars in the earlier days. We still do that, but as I said, maybe there are pulsars which doesn't emit regular train of pulses. So when you take a Fourier transform, if you don't have enough number of pulses, the Fourier transform energy will not be enough for you to say there is a periodic signal in there. So you start looking at the data from single pulses. You see that whether even if there are no periodic pulses, maybe there are single bright individual pulses there. So people are just exploring another domain. So we are not really leaving the way we are doing the pulsar searching. We are just kind of adding a new tool by looking for single pulses as well.
Okay, sir, got it.
Okay. So since now we knew that there was this one FRB which was repeating, now we can do something very good. You can use interferometer. So interferometer have this capability that they can pinpoint direction of any radio source within milli-arc second or arc second accuracies, which is pretty good. If you are able to do that, that means maybe you will be able to find out which galaxy that is coming from. And that's precisely what they did. So in 2017, they used the Very Large Array in New Mexico, and they pointed towards this one repeating FRB for many, many months, and they got lucky. They detected few bursts, and not just that, they detected some very bright bursts, and based on that, they were able to pinpoint the location within milli-arc second accuracy, which was pretty fantastic. Because once you have that kind of precision, now you can go to the optical domain. You can look at the optical data and see whether there are any associated galaxies in there. And they found it. They found that there is in fact a galaxy at the precise location on which you found these repeating FRBs or repeating bursts to exist. So what I'm showing you in this plot, this is obviously the dispersed pulse that was detected with the Very Large Array. And this was the localization that they were able to achieve. Just ignore, I think this is not really relevant at this point. But this is a precise location of the fast radio burst. Again, showing you the precise location in this square box here. And they found a galaxy. This is the optical image. They found a pretty tiny, a low metallicity galaxy at this point, which was pretty good. And this was the very first time that fast radio bursts had association with a extra galaxy. So earlier, before this, you can always argue maybe our understanding of interstellar medium is not complete. Maybe their dispersion measure that we are seeing for this burst, maybe they be coming from still within our galaxy, but we don't know. But this was a very first evidence that they are truly extragalactic, because now you know they are in fact coming from this galaxy. So not only that, what we could do is that we could measure the redshift of this galaxy using optical spectra. And once you measure the redshift of this galaxy, you can measure how far away they are, obviously. And then you can calculate the dispersion contribution of intergalactic medium, and that matched pretty well. So that was clear-cut evidence that in fact, they must be coming from this galaxy itself. So this was again some more sort of detection, which find that the FRB was located in this galaxy. So this is an image of the galaxy, and the cross is showing you the detection of the fast radio burst. So some of the interesting fact about FRB 121102, it is the only known FRB at that point to repeat. It was localized to a dwarf galaxy, which was 1 billion parsec away at the redshift of 0.19. A deep radio observation. So people also did radio observation of the galaxy, deep radio observation. And they found that there is, in fact, a bright, prominent radio source, continuum radio source associated with the location of where the fast radio bursts should be associated. So that is shown in this image. You can see the bright radio source here, and the cross over here is showing the position of the fast radio burst. In fact, they were able to find out that this persistent radio source is less than 40 parsec away. Think about this. This galaxy is 1 billion parsec away from us, and we are saying that the fast radio burst is coming from this associated radio source within 40 parsec. 40 parsec, maybe it's large number from the galactic scale, but it is pretty small compared to when you think about it there, that these galaxies is like 1 billion parsec away from us. So this is quite phenomenal. And that gives us a pretty nice clue about where they must be coming from. I'll just skip to some of the high energy part. So far, what do we know up to 2070? I'm just talking about 2070. There is a whole lot that has happened after that, but I'm kind of going in a more historical sense and throughout this talk. So FRBs, now we know, are millisecond duration, highly dispersed, extragalactic energetic bursts. Up to 2017, 30 FRBs were known with quite large dispersion measure. But there was something very missing about FRBs. Only 4 FRBs were detected at 800 megahertz, while most of them were detected at 1420 megahertz. So there were some interesting questions about fast radio bursts. What is the spectra about fast radio? Because you can say a lot about the emission processes if you know the spectra of the fast radio burst. So we didn't know at that point that do fast radio bursts emit at large range of frequency? Do they emit at low frequency? Do they emit at high frequency? We had no absolute idea. What are the high time resolution studies? Like, can we really look at these individual bursts in a more finer detail? What are the different things that we will be able to see? What are the polarization properties? So there were only 3 or 4 FRBs for which the polarization properties were measured, and they were quite inconclusive. We measured some high degree of polarization in some cases, but in some cases we were not able to measure any polarization at all. Polarization is a very important clue in understanding the emission processes. So there were still some of these open questions in 2017, and fast radio bursts were a booming field, but with these questions in mind. Any question till that at this point?
Sir, I didn't understand that point that the galaxy is 1 billion parsec away and the fast radio burst is coming from a distance less than 40 parsec away. What does that mean, sir?
Oh, maybe I can kind of explain it pretty well. So what I meant was that the 1 billion parsec away, there is a galaxy. In that galaxy, when we make a radio image, we found a bright radio source, and we measured the location of fast radio burst with a projected distance of 40 parsec from that radio source. But both of them are still 1 gigaparsec away. It is just the distance between these two sources in the sky.
Okay, sir. Okay, sir.
So does the intergalactic medium affect the polarization of the light?
It does, but to very small degree. It doesn't affect it by a lot. So polarization is largely affected by the magnetic field, and intergalactic medium magnetic fields are not that strong to really affect it by a large degree. It's primarily affected by the source's local environment or the local host galaxy magnetic field or our own galaxy, but not so much by the intergalactic medium.
If we study the polarization of the light coming from that source, how can we ensure that it's not something in the line of sight, like our galaxy, suppose, or something else which is somehow...
Yeah, you can basically, similar to dispersion measure, you can measure. I mean, I'll come to that. Maybe I'll explain when I come to that slide.
Okay, thank you.
Sir, why can't fast radio burst occur within our galaxy?
I'll come to that. Any other question? Okay, let's move. So I'm part of this project, called Breakthrough Listen. So I guess so far it is clear, right? So up to 2017, we knew something about FRBs. We knew that they are large, they have large DM, but there were lots of these open questions. These are hard questions to answer. You need resources, computing resources or computing backend, which has that kind of flexibility to do all this. For example, for doing high time resolution studies, for doing polarization studies, you need, if you want to do polarization studies, you need to have, for example, access to raw baseband voltages. If you want to study spectra of the pulsar, you need high sensitivity instrument which can observe these pulsars which can observe these FRB at higher frequencies. So that didn't exist. Fortunately, there was this project named Breakthrough Listen, which I'm currently part of, which is one of the most comprehensive and sensitive search for evidence of intelligent life in the universe. And I'm happy to talk about it at any other time if people in the audience are interested in talking to me about how do we basically search for this. But what does Breakthrough Listen do? So we have a 10-year sort of contract, and we have $100 million given to us by generous grant from our donor. This project was initiated in 2015 with Professor Stephen Hawking, who was also, and Marty Rees was being a prominent sort of member of that group and being our advisor throughout the sort of program until, unfortunately, passing of Professor Hawking. So this program is doing this extensive searches for various different objects to search for evidence of intelligent life. And for that, we have deployed some of the most state-of-the-art computing resources at some of the most large radio facilities. So the telescope that I'm showing you in the left is the Green Bank telescope in West Virginia, which is 100 meter in diameter. It's just one of the biggest sort of steerable radio telescope in the world. And at that telescope, we have installed a 64 compute node cluster, which is able to capture something around 12 gigahertz of bandwidth. The typical radio telescope, or most of the radio telescope that you do, the bandwidth that the instrument is able to capture is limited. But we had the capability of capturing a large amount of data, a large amount of bandwidth, because we had that resources available to us. So with that, I designed this pipeline to search for fast radio bursts using the Breakthrough Listen backend. And I'm from India, so I named this pipeline Spandak. Spandak in Hindi, I guess, means pulsating objects. It's a GPU accelerated pipeline. It uses the GPU to search for these dispersed pulses. As you can see, the dispersion, as I think at the beginning, somebody asked this question that what if the dispersion is so large, doesn't it make it difficult? It does make it difficult to search for them. And that's why you need GPUs. Not just that, you also need machine learning. So my pipeline does both. They use GPUs. They also use machine learning in order to find and search these FRBs. So we had this capability and we applied it. And we thought that, okay, like, why not we search for fast radio bursts at higher frequency towards this one known repeating fast radio burst. So 12102 I mentioned earlier, which was already localized to a dwarf galaxy. So we know precisely where to look. We pointed our telescope for 6 hours and we got lucky. We detected something around, at the first instant, we detected something around 15 bursts. This was the highest frequency detection of fast radio bursts ever. And I'm kind of excited to say so far this is the only detection, because people have tried to search for FRBs at high frequency, but there has not been any success. So fortunately, unfortunately, this was the only detection that ever happened of fast radio bursts at the highest radio frequency. So this is just showing you kind of an animation of different pulses that detect, and you can see that the frequency is labeled in the y-axis here. You see the frequency is 8 gigahertz, starting from 4 to 8 gigahertz, and you can see a pretty nice dispersion sweep. So this is the way we kind of detect them. And this became quite popular because since I was part of the Breakthrough Listen, and when we announced the discovery, they thought that we found alien. So lots of their news article came out at the time which suggested that we found ET, we found 15 mysterious bursts from ET, which was not really true. This was actually a well-known astrophysical object, and we didn't really find ET from it. But obviously, the media kind of ran with it. But there was something pretty interesting about these sources that we detected. So as I said earlier, some things were not very known. Like, for example, we didn't know about the spectral properties. So we at least were able to find the FRBs bright enough at high frequency. But although along with that, we had the capability of looking at these fast radio bursts in extremely finer detail. So in my paper, we actually we're able to resolve the individual pulses. So this is just one pulse, but now we are looking at this pulse in a much fine time detail. And what we found was something spectacular. We found that the bursts have multiple sub-bursts in it. So individual burst is not just one burst. It is made up of multiple sub-bursts, and the emission frequency of these individual sub-bursts are quite different. And they progressively kind of downward drift. So the time is moving from left to right. And you can see the more of the leading edge pulses tend to have emission at a high frequency, but as you move to the later bursts, the emission kind of slowly drifts to lower and lower frequencies. We found that in a couple of bursts, which was quite interesting. So this was a very mysterious sort of phenomena that we noticed at the first time. We also found that the substructure are of the order of 30 microseconds. So if you see something that is 30 microsecond wide, it means that the emission region itself should be pretty small. That means the emission region itself should be less than 10 kilometers, which is quite spectacular. Think about this, that these objects are located like a billion parsec away from us, but we are saying the emission is produced within just 10-kilometer region. That's just amazing. Now, somebody was asking about the polarization about it. So before 2017, nobody knew much about the polarization property. So let me kind of briefly explain what do I mean by that. So this is again classical pulsar, beam of radio emission pointing towards us. You see a pulse, and this is just showing you a cartoon animation of the emission beam, and the red line is showing you a line of sight. So basically, you're not seeing the entire beam, right? You're only seeing a part of the emission beam as your line of sight kind of passes through that. So you can measure the polarization angle based on your line of sight, and you can measure how far the polarization angle moves from one side of the pulse to the other side of the pulse. And you can also measure the rotation measures. I'll come to that. So when we looked at the polarization first, we didn't see anything. So the red line here is supposed to show the linear polarization, and the blue line is supposed to show the circular polarization. But when we started looking at the polarization, we didn't see anything. The mystery was that it is because of the rotation measures. I think somebody was asking this question. What is the intergalactic medium, or what are the effects that changes the polarization angle? So these are the things which changes the polarization angle, but that changes is very much frequency dependent. This is what we call a Faraday rotation. So let's say you have a pulsar, which is emitting pulses in a one sort of linear polarization fashion. But now when it passes through the interstellar medium or the maybe the local environment, any magnetic field, that magnetic field rotates the polarization angle, and that rotation, the delta PA, is frequency dependent with a term which we call rotation measure. And rotation measure is, you can see, you might remember this equation from earlier. Only thing that is added here, this is similar to dispersion measure, but now you have a parallel magnetic field component associated with it as well. So the rotation measure is similar to the magnetic, similar to the dispersion measure, but it also kind of adds whatever is the line of sight added magnetic field component with that. So that introduces the change in the polarization angle, and you need to correct for that. So you need to know what is the rotation measure. Once you know the rotation measure, you can correct for that, and then you can recover the loss polarization from this pulsar. So you can, similar to dispersion measure, you can do rotation measure trials. And we did that, and we found that the rotation measure was extremely high, something around like 10 to the power 5 radian per meter square, which was never been observed to any other astrophysical source. But when we correct for that, we recovered almost all 100% flux. So now you can see that the red line, which is a linear polarization, is as high or as equal to the black line. The black line is the total intensity, and both of them are matching, which means that all the energy that is being produced by this FRB is 100% linearly polarized, which was spectacular. Nobody knew about this, and this was the first discovery at that point. So there are quite few implications of these findings, and I will kind of stop and take question after my 2 slides, so just wait for it. So what I'm showing you in this plot is the dispersion measure as a function of rotation measure. And all the black dots that you're seeing are the pulsars, radio pulsars that are all within our own galaxy. So we know the dispersion measure, we know the rotation measure, and you can basically plot them against each other. Basically, the relation is pretty straightforward. Rotation measure is just simply this, and dispersion measure is without the B term here. What was most interesting was that all the other objects, these are all galactic sources, and there are a few FRBs which had a high DM but pretty low rotation measure. But FRB 121102, although we didn't know the dispersion measure coming from the galaxy itself because there was some ambiguity in that. So that's why the dispersion measure range is shown with a line. But what you can see here is the rotation measure. The rotation measure is quite high. In fact, these are all the different astrophysical objects. None of them go as high as FRB 121102. So the first implication was that first, that obviously I mentioned earlier, that we found that the source is located in a very dense, is a compact objects. Another reason was that another finding was that we found the highest rotation measure, which means that the source is embedded in kind of a highly magnetoionic environment. So highest RM suggests that source of FRB is compact objects in a highly magnetic ion. So that's what I guess you would probably like to remember. A couple of more things. We also noticed that the RM was not constant, it was changing. So over the years, when we measured the RM, we noticed that the RM was changing, but DM was not changing. So again, just kind of reminding you the equation of DM and RM. Basically, DM is just electron density and RM is electron density with the magnetic field. So if the RM is changing and DM is not changing, that means definitely the magnetic field is weakening. Definitely, magnetic field is kind of declining. So we measured, this is the RM observed as a function of time, and different data points that you see are indication of the measured RM. And as you can see, that has gone down over the years. This was a huge discovery that large RM without changes in DM implied that large contribution from compact objects, compact region with high magnetic field. Neutron star, it could be the neutron star is in the vicinity of some kind of a black hole or some similar like galactic center magnetar. So this was one of the major discovery at that point, because this kind of gave us a clue that the FRB, at least the one FRB that we measured, is located in a highly magnetoionic environment with extremely high magnetic field. And that was something pretty exciting. So we wrote a Nature paper. In fact, Nature was so happy with that they allow us to write, they also put us in the cover. And we had a press conference in Washington, DC, announcing these results because this was a kind of a path-breaking discovery in this field. Right, so I think we are at the time, and I have a couple of more slides to go, but Sykes, let me know what you want to do. Should I continue or is there another thing planned?
No, I think you can continue for a little while. I think it should be okay. I mean, all of us are enjoying your lecture actually and all the exciting results. So I think just continue for a little while.
Okay, sure, I'm fine with that. So I guess before I move on to the next step, if there's any question with this? I'm not following any chat discussion, by the way. So, but if there are questions, please.
Be parallel. Parallel to what?
Line of sight.
So, sir, so have we completely mapped out the magnetic fields in the line of sight? Because if we want to calculate this measure, then we need that, right?
Yeah, I mean, we roughly know the contribution from the line of sight, from the intergalactic medium based on other measurements. So that is just inferred from that. But the contribution from the intergalactic medium are going to be the order of 10 to the power minus 4 or 5 radian per meter square. So they are no way close to what we were getting. So most of the, in fact, from our own galaxy, the contribution of rotation measure towards that line of sight will be of the order of 100 or 200 RM. So the RM, for example, towards this part would something of the order of like few hundred. But if you're getting the RM of the order of 10 to the power 5, that's just pretty high. That means that it is definitely coming from local to the source environment itself.
For the RM, do we need to rigorously like calculate weak parallel, or are we just trying out different RMs and see what best the signal to noise ratio?
Yeah, that's the best way to do it. We basically measure the rotation measure by correcting for different trial RM and try and recover the maximum polarized flux. So this is the polarized flux as a function of rotation measure. And wherever we get the maximum, that's the rotation measure is supposed to be for that source.
So what was del PA? Could you just repeat that?
Sorry?
Del PA in the equation which you just showed for RM, it was written del PA equals, yeah, that one, lambda square into RM. So what is this del PA?
Oh, so PA means the polarization angle. So let's say you have a source which is emitting at some polarization angle. When you receive the signal, you receive it at a slightly different polarization angle. So delta PA correspond to the changes in the polarization angle. Not just that, but is also changes as a function of frequency. So delta PA corresponding to that. So how much is the change in the PA as a function of frequency you are seeing due to the rotation measure? Okay, I have a couple of more slides which are pretty interesting as well. So I'd like to go on to that.
In case the radio burst which is coming, it travels like there's some highly magnetic source in between. So then the RM would be very high, right?
It can contribute from the intervening medium, but so far we don't see any intervening galaxy basically you need to have some galaxy, or you maybe need to pass through a center of another galaxy. Then you will have a high magnetic field coming from, maybe there is some, maybe the supermassive black hole at the center of any galaxy may give rise to the extra magnetic field. But in this case, the line of sight is pretty clean. We don't see any intervening galaxy that could contribute. So not only that, I had a student who was working with me at that time, and we thought that we do something strange, we do something different. So far, most of the FRB before this were discovered using the standard sort of tool, the GPU tool that I mentioned earlier, that tool that I guess I also wrote. But we tried to do something different. We use the machine learning or the convolution neural network to identify fast radio bursts, and we got quite lucky. It performed pretty well. In fact, even better than our classical tool, because some of these fast radio bursts were not very broadband. This is a very particular feature about FRBs, but FRBs are not very broadband. They actually have emission which are concentrated in a very limited frequency range. They are pretty narrow band in that sense. So our classical tools were a little bit less sensitive to detect them, but machine learning tools were quite effective. And in fact, we were able to detect 100 of new fast radio bursts from the same source using the machine learning tool. And in fact, this also came out as quite, it was pretty well announced in a media as well, that artificial intelligence helped us discover fast radio bursts. Okay, so this was a time when only one fast radio burst was known, but later it all changed because the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, changed the field upside down. Before this, we had a few handful of FRBs we knew, but when CHIME came online and when it started making discoveries, it was just completely blew us all off. First of all, it found another repeating FRB, which also showed similar downward drifting emission pattern. Although CHIME was operating at much lower frequency than what we had discovered, CHIME was operating at some between 400 to 800 megahertz. But this downward drifting emission pattern was still present, which means that this is something peculiar about the repeating sources, that they have this particular emission pattern. Maybe it is associated due to their origin, that somehow they are being originated in a way that is giving rise to this particular emission pattern that you're seeing. Similar, you can see that their first component is bright at high frequency, and as you go to lower and lower component, the emission kind of switches to lower frequency. This is also known as a sad trombone, like ta 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 ta, kind of like that you can assume. So it's similar to like our 8 gigahertz feature that we have noticed. Second repeating FRB also showed the downward drifting behavior. Not just that, so far we know 24 repeating FRB from CHIME, all of them, most of them have been found from CHIME. There are other been found from FAST as well. But the field is booming. When we first made our observation, we only knew one FRB, which was repeating. Now we know there are 24 of them. So what does that mean for all of this? If there are more repeating FRB, that means that some of these cataclysmic model, which really destroys the source itself, may not be the likely explanation, because in order to produce the repeating sources, you need the source to survive. You can't really destroy it. Like you can't really have collapse. You can't really have a merger, because that can't be repeated. And if you have repeating bursts, that means that all of these cataclysmic models are unlikely to explain the fast radio burst. So then what else is out there? What else can give rise to fast radio burst? Current model favors that FRBs are in fact neutron star, because as I mentioned earlier, that they are compact objects. So what do we have in compact objects? You have neutron stars or you have black holes. typical neutron stars have extremely high magnetic field, so they are pretty good kind of contender for this. And in fact, the extreme form of pulsar are called magnetar. So they have something of the order of 10 to the power 14 or higher magnetic field. So they are extremely bright. They're extremely sort of active in magnetic field. So they are called magnetars. So maybe the FRBs are magnetar, and the emission that you are currently being produced could be associated with some kind of a magnetic field interaction similar to pulsar, but obviously pulsar emission cannot be as bright as you are seeing, as I mentioned earlier. So you need some extra effects in there, and that is still a mystery. People are still trying to figure it out. What are the extra features that might allow to pump the extra energy into pulsar to produce this kind of bright radio emission? So there are various models still out there, but most of them still favors neutron star or magnetar. The only difference between them where exactly the emission is being produced. So whether the emission is being produced in a closer, so this is your neutron star and this is the radio beam. If the radio emission is produced somewhere closer to the neutron star or far away, that is still a question. Like for example, there are models which suggest that for example, like this is a neutron star. Let's say it kind of produces some kind of winds, and neutron star, because they are born after supernova remnant, after supernova explosion, it is likely that they are maybe still inside a supernova remnant. So they are inside this thick shell, and the shell is expanding. So when this neutron star produces this bright sort of burst, they could interact with this shell, which can give rise to the FRB. So there are models which seem to suggest that as well, that young magnetars, so these are young systems which are interacting with its surrounding medium, which is giving rise to the FRB. And then that was it. So then there was a flood of FRB. So in fact, CHIME changed the whole picture. Every radio telescope in the world right now is probably looking for FRBs. There are programs going around across almost all the radio telescopes look for FRBs. And that's how that whole thing has changed. Like, for example, this was the case in 2017. Like, we knew about few FRB. This is just a distribution of fast radio bursts in the galactic coordinate. And there are a few FRBs here and there, some repeating FRB that we knew. But now this is the current picture. This is just absolutely phenomenal. We now know something around 600 fast radio bursts. 24 of them are known to repeat, and they've been discovered from large number of radio telescopes. This has completely changed our understanding. Moreover, these FRBs are now useful as well, because earlier we only knew about few of them, but now we knew a lot of them, and we are also able to pinpoint where they are coming from. So because of that, we could measure the intergalactic medium more precisely. Because, for example, if you measure the distance where the host galaxy, we can measure how much contribution the intergalactic medium must be making. And that allows us to actually calculate the baryonic content of the local universe. This is kind of fascinating. Think about it. So localization has been a game changer. I think we have localized something around 20 FRBs. What do I mean by localization? So there are telescope in Australia called ASCAP, which has been a primary driver for these localization. And they have found many FRBs to be associated with different kind of galaxies. So basically, the localization is pretty important. If you remember earlier, I mentioned that there was just one repeating FRB, and people used that to localize it to this one tiny dwarf galaxy. But now we have 20 FRBs which are localized, and they come from range of different galaxies. So in fact, this has muddled the water a bit. If it was all similar type of galaxies, it was pretty nice. We would be kind of have a pretty less explanation to do, but now the range of galaxies that we see is so large that any one model is pretty hard to fit to all of these different kinds of sort of scenarios. We see galaxies which are low metallicity. We see galaxies which are kind of like our galaxy, for example, like spiral galaxies. We have detected FRBs in galaxies as well. In fact, the closest FRB, the extragalactic FRB that we have detected is in M81 globular cluster. That is shown in the image here. So even people have found FRBs in the globular cluster of another galaxy, of our nearby spiral galaxy. Again, this is all kind of fascinating to give us some idea about where they must be coming from.
So the circles are the localized positions, right?
Yeah, and the cross is the center of the galaxy.
Right.
Yeah.
not related to this slide, but earlier you said that the FRBs are at this particular frequency. So what does that mean when they emit a range of frequencies?
What does that mean? So it means that we detect them at that radio frequencies.
You said that earlier that some were at 800 megahertz, 1420 megahertz, but was that relation also about the dispersion delay?
No. This is apart. This is actually outside of the delay. So even if you correct for delay and everything, some FRBs are not even visible at different frequencies. So people have tried to look for FRBs at range of frequencies, but FRBs are pretty frequency limited. So I guess you can see it in this plot as well. Like for example, this burst is bright only below 7.5 or 7.5 gigahertz, all the way up to like something maybe like 5 gigahertz. But if you look at outside of this frequency, maybe if you look at this frequency, you don't see the FRB. Or if you look at low frequency, you don't see the FRB. I don't know whether that answers your question. So the FRB itself is not emitting at these frequencies. So it is kind of contrary to what we know about pulsars, because pulsars are pretty broadband emitters. We don't really see pulsar being absent at one frequency or reverse versus the other. They are pretty broad and they are pretty visible at all frequencies. But FRBs are quite different in that sense. They are only bright at some frequencies while they could be completely absent at all the other frequencies.
Okay.
So these frequencies are what we detect, right?
That is correct.
So they might be emitted at some other frequency, right? Because of redshift.
Sure. Oh, not. I mean, well, not due to redshift. This is just the emission itself is bright enough for us to detect at a given frequency. I mean, we are observing, every radio telescope is observing a very small part of the frequency band. For example, like take an example of GMRT. GMRT can do 200 to 400 megahertz of bandwidth. So it can only observe within this small frequency window. If the FRB burst is happening in this window, you will catch it. But if it's happening outside of this window, you might miss it. Some of the clever way you can do is that you can maybe start putting half of your antennas at one frequency and half of the antenna at other frequency, and maybe see that, okay, maybe there are pulses that is bright in one band and not in the other. You can do some things like that. But it is just the emission itself. It is not due to the redshift or any other effect.
No, but I think you would agree that if you see it at certain frequency sitting on the Earth, then the emitted frequency.
Oh yeah, sure. That is.
So all the inferences you might want to draw later for commonality of something should take into account the redshift.
Definitely. No, that is of course. Once you measure, but that has only been possible to do for galaxies, for FRBs where you have localized them.
Sure.
If you have measured the host galaxy redshift, then yes, you could correct for that. But if you have not measured it, then it is just a guessing game.
Yeah, based on the distance.
Yes.
For the 28 galaxies we have localized, do we have an idea of what frequency, at which frequency the radiation is actually emitted?
So because it all depends on, it's a very selection bias effect, because most of these localization has been done at 1.4 gigahertz using this telescope ASCAP. So most of these localization have been done using a single telescope or array of telescope, which is ASCAP. So most of them are done with 1.4 gigahertz.
So there might be some selection bias.
Possible. Yeah.
But
I don't have a plot of their redshift distribution, but they are not that far away. Most of them are within one redshift, which is exactly equal to 1. They are not that far. Yeah.
So these sources emit only in the radio particular band. Like if we use maybe an X-ray telescope or a like X-ray satellite or a gamma ray satellite or something like Hubble, they won't be able to detect this.
Yeah, that has been a mystery, because some of the earlier models seem to suggest that radio should follow X-ray or gamma ray emission. So there may be a radio or X-ray or gamma ray flare that we might be able to detect based on what model you are subscribing to. But so far, there has been lots and lots of follow-up in X-rays and gamma rays of many of these FRBs, but no success. We have not detected any of them outside radio.
Sir, you told that like many theoretical models are ruled out due to the repeating nature of some FRBs. So can it be the case that the FRBs which are not repeating might obey those theoretical models which are ruled out?
Definitely.
And
So no. So that is a current debate in the field, that are there two mechanisms of generating fast radio bursts? One which generates a repeating burst, another which generates non-repeating burst. But I guess if you take Occam's razor, two mechanism generating exactly similar kind of burst, because we have seen some non-repeating FRB to also show similar kind of morphology that we see in a repeating FRB, like these downward drifting emission pattern, this critical nature of repeating FRB that has been seen in non-repeating FRB as well. So unless there are two mechanisms which are very much far away from, separated from each other, but producing emission in exactly same manner, it is hard to kind of have two different models to explain the fast radio burst phenomena. But it is there. I mean, obviously, people do argue that there are two models, and in fact, during one of the recent conferences, there was a poll taken. I guess there were like 200 or 300 participants, and it was 50-50. I guess there are some people who believe or expect that there may be more than two models. Some people think that there is just one model which produce all the FRBs, but it is not yet completely sort of ruled out.
So why are these FRBs extragalactic? Like, why aren't they found within our galaxy?
I'll come to that. That's a good question. That's to my next slide. So unless there are any other question, I'll go to the next slide. Okay. Sorry, is that a question?
Yes, sir. So could like you said, these FRBs might be like some condensed object in like our universe. So could they might be the first case of the white holes? Like they might be
white holes have been, they have been theoretically predicted to be one of the sources for the FRBs. Yes, but I don't know much about white holes to really answer your question.
Okay, sir.
If you guys are interested in kind of studying more about this, I'll suggest you to go to this website called frbcat.org. And that has a list of all the different theories that people have suggested for fast radio bursts. And you will find one of that is also mentions the white hole. And maybe you can, there are a couple of papers which favors and suggests that maybe you can feel free to read it. There are 50 or 60 models out there. So obviously I have not gone through each and every one of them. So depending upon your interest and your sort of favor, you can choose what model you think might be kind of could explain it, and you could read depending on that. But there is a table of all the different theories that people have proposed to explain FRBs in this particular website. They call frbtheorycat.org. So because this was a question I guess somebody asked, and so I just want to kind of wrap it up with this. So yeah, people ask us like, how come we have not detected FRB in our own galaxy? So if you take the rate of fast radio bursts, typical in a local universe, which is happening at like 2,000 or 3,000 FRBs every gigaparsec cube in a year, the chances of that happening is pretty rare. That means like once in 100 years, such event must be happening in our own galaxy. But maybe it's higher because we got lucky. In 28th of April 2020, when the whole world was shut down and like people were working from home, there was this one event happened which kind of changed everything so far we know about FRBs. This was detected. There was a one fast radio burst event detected from very small telescope. This you can see this is very tiny sort of telescope. But the idea was that they placed this telescope quite far away from each other. So any kind of local interference that might come in will not really interrupt it. So if you detect even even smallest amount of sort of radio flux, but it is persistent, it is kind of consistent with 3 of different antennas which are placed far away from each other. This is in California, and 2 of them are in California, one is in Utah. And you can basically triangulate the position. So they did that and they triangulated, they found a bright radio pulse, which was, if you infer their sort of calibration, mega Jansky, so 10 to the power 6 Jansky. So it was super bright. In fact, the Chime telescope in Canada also detected it, even though it was far away from its main lobe, because it was so bright that it was detected. And that source is a well-known magnetar. So that's within our own galaxy, because we can measure the dispersion measure of it. We knew, so this was the source that was detected. It has some kind of a downward drifting, but the other way around. So we detected two pulses, or like one pulse, but if you resolve it, there are two pulses in it, and they are basically mega Jansky wide. So which means that maybe, but this source is very well known. This is actually a magnetar. We had already knew about it. We had studied them in the past, but nobody knew that this source will emit such bright radio pulse. It was not predicted, but we found it, which means that maybe the magnetar is the missing link, and this SGR is the missing link. So I guess somebody was asking this question about what is the typical energy output of radio pulsars and what is the total and compared to the fast radio burst. So I just want to show that in this plot. What I'm showing you in this plot, on the x-axis is the typical transient duration, like what time interval these typical events last. So they are typically last for like a millisecond or so. And what is the spectral luminosity, like hertz per second per hertz? The typical pulsar sits at something around 10 to the power 19 or 20 or 22 up to all this level. But fast radio bursts are much, much more brighter. They are 10 to the power 33, 34 hertz per second per hertz. I mean, you divide it by hertz, so that's why the 10 to the 42 hertz per second is now come down to, because you divided by megahertz, so it came down to like 34. But it is quite bright. And the fast radio, the galactic magnetar that we detected produced many pulses, which seem to kind of fill in this particular gap. So maybe this is the missing link. So the galactic center the galactic magnetar give us a clue that FRBs could be young magnetar. But I guess somebody was asking this question: what about the period? So because it's a magnetar, it's a rotating. It should be similar to like pulsar. It should produce pulsation in a periodic fashion. What about this? So typically in pulsar you see pulses, but we haven't seen any pulses. So this is our, for example, from my detection of 121102. And we see these pulses, but there is no periodicity. We try all sorts of fitting, all different ways of fitting a period. We didn't find any period. So there is no periodicity associated with it until there was this discovery of this one source. We found a periodicity, but it is not the periodicity that you would like. It was a 16-day period. And it was a period in a way that you only see the activity of fast radio bursts to be more prominent as a function of days. So, and that they seem to repeat every 16 days. So every 16 days, this FRB seem to become active and produce pulses, and then they go off. So what I'm showing you here on the x-axis is the time, and this is the kind of exposure time that is shown, and all the gray lines that you see are the ranges of period, and they are all separated of 16 days between each other. And the red triangle shows the detection of pulses, and you can see they all happen to occur within the 16 days period with each other. And this is a Fourier transform, again, peaking at 16-day period, which was quite interesting. And people kind of thought about various models that, for example, maybe the FRB is rotating around like, for example, maybe a black hole. And there are kind of other companion, which has some winds. And these winds, when it kind of comes to you see fast radio bursts. Or maybe there are other precision model that may suggest that there are other ways by which you can have periodicity. But very recently, using GMRT, one of my students found the same fast radio burst at extremely low frequency. In fact, the same pipeline that we use Pandak to detect fast radio bursts at the highest frequency was also used to detect fast radio bursts at the lowest radio frequency. So we did that with two radio telescopes, one with the Sardinia radio telescope and one with the GMRT. So one of my students detected this with GMRT. And it kind of suggests that it means that if you detect the fast radio burst at extremely low frequency, it means that the environment around which the fast radio burst is being produced is pretty clean. So that might constrain the models of some of these periodicity. For example, if its companion is producing lots of wind, that wind is not disrupting the emission itself. The environment is clean, that the radio emission is able to move freely through it. Okay, so just final summary slide. So I guess I started with this three main questions, and I kind of trying to answer this here. So what are they? What are fast radio bursts? They are millisecond duration, highly energetic bursts, dispersed burst, extragalactic burst. Where do they come from? They are found to originate from a range of different types of galaxies and environment. Most likely explanation is that they are magnetars possibly in a binary orbit around black hole or other companions. How are they useful? So they, first of all, they allow us to understand extreme physics. Like, for example, as I said, we don't know what processes can give rise to such bright radio emissions. So understanding them allow us to understand the nature, the physics itself. And finding and localizing them will also allow us to understand the intergalactic medium, because once you localize them, you can study the intergalactic medium, you can study the magnetic field in the intergalactic medium, and a whole range of sort of things that you could study about our universe. So they are quite useful in that regard. So I think, yeah, so this is the last slide. So I hope I was able to convince that fast radio bursts are some of the most exciting astrophysical objects, and it's quite fascinating to kind of study them.
So when we look at a fast radio burst for the first time, how do we know that it's going to repeat, or there is going to be a periodicity?
We don't know that. So typically most of fast radio bursts, so either you do a blind search, which means that you really just simply point your telescope towards an empty part of the sky and you observe for long duration and expect that there will be a fast radio burst happening. Or if you already know that there is a fast radio burst, a repeating fast radio burst found in that particular part of the sky, you point your telescope to that part of the sky and you observe it for long duration. That's the only way.
Sir, are these bursts by any means dangerous for us? Like, can they affect our environment?
Not really. The energetics is in like few Jansky, right? So they are far less energetic than typical flux that you get from our sun. I mean, they're not really that. Definitely not really dangerous.
So thanks, Vishal, for a absolutely fascinating talk, and a lot of discussions as well. Thanks very much.